Hi everyone! Welcome back to integralcalc.com. Today we're going to be doing another Green's theorem problem, and in this particular problem we've been given two functions, p of xy and q of xy, with p of xy equal to y plus e to the x and q of xy equal to 2x squared plus cosine of y. We've also been given here this line integral that's defined by the three corners of a triangle. 0, 0, 1, 1, and 2, 0 are the vertices of the triangle, and they define the triangle here in the first quadrant of our graph, so I've gone ahead and graphed them. But what we've been asked to do is find the area bounded by this line integral. And keep in mind that when you're doing a Green's theorem problem, you're usually given the problem in one of two forms. You're either given the two functions p of xy and q of xy as we've been given in this problem, or you might be given something that looks like this line integral here, with the two functions already plugged in. And if that's the case, it would look like this. You'd have the functions. What you would want to do is recognize p of xy here, and q here. So p, remember, is in front of dx, and q will be in front of dy. So either way, whether you're given the line integral or the functions themselves, you can extract the functions from the line integral so that you can identify which one is p, which one is q, and then start taking your partial derivatives. But remember that Green's theorem allows us to convert this line integral into a double integral so that we can evaluate the area. So this formula here for the double integral is what we're going to be focusing on. And notice that to use this double integral, we're going to need the partial derivative of q with respect to x and the partial derivative of p with respect to y. We'll also need to fill in upper and lower limits of integration on both of these integrals here and replace this dA with dy dx. But we'll get there in a second. So the first thing we're going to do is take the partial derivative of q with respect to x and the partial derivative of p with respect to y. So when we take the partial derivative of q with respect to x, remember that we're treating y as a constant and x as the variable. So q is 2x squared plus cosine of y. So with respect to x, that gives us 4x plus 0, which of course is just 4x. That cosine of y becomes 0 because remember y is a constant. When we take the partial derivative of p with respect to y, again we treat x as the constant and y as the variable this time. So we'll get 1 plus 0, which of course just gives us 1. So now that we have these, we can go ahead and plug in, and we'll use the same colors here. So we'll use blue for the partial derivative of q with respect to x. We're going to plug it into the formula this way, and the partial derivative of p with respect to y is going to plug into our integral here. So let's go ahead and start converting this line integral to a double integral. So I'll write my double integral notation here. I'm going to leave some space, remember, for our upper and lower limits of integration. So I've got that there. Now q, partial derivative of q with respect to x, is going to be 4x minus partial derivative of p with respect to y, which is 1. And I'm going to go ahead and put my dA in there. This dA is actually going to get replaced because our inner integral is going to represent y, our outer one is going to represent x. Remember that when that's the case, we have to, because y is the inner integral, we have to have dy here on the inside, and then x is the outer integral, so we have to then have dx here on the outside. So we replace dA with dy dx to match inner, inner, outer, and outer. Now all we need is our limits of integration. This is where this problem gets a little bit trickier than some other Green's theorem problems because we've got this line integral, right? We've graphed it here, and it represents a triangle, right? The line integral bounds a triangular region. Well, unfortunately, we can't just evaluate the area inside the entire triangle because we essentially have two regions here. This triangle is cut in half, and the reason is because this line here is represented by a different equation than this line here. Than this line here. So we need to evaluate this in two parts. And what we're going to do is evaluate this region first, right, half of it, And then we're going to evaluate the second region over here. And what we'll do, our upper limit of integration for this line region, right, is going to be this equation here. That'll be our upper limit of integration. Our lower limit of integration will be the x-axis here, this line, and that's going to be y equals 0. For the teal region, I guess you could call it, we'll have some other function, g of x, which we need to find. That'll be our upper limit of integration. And our lower limit of integration will be this line here, which again is going to be y equals 0, right, the x-axis. So we just need to find f of x and g of x. So f of x we know to be the line, we'll write it out here, f of x we know is the line y equals x. And the reason is because we have 2 points on it, 0, 0, and 1, 1. And we know that that line intersects or bisects the first and third quadrants exactly, and so the line is y equals x. You could use the equation y equals mx plus b, plug in your points 0, 0, and 1, 1, and find that equation y equals x. And in fact, let's go ahead and do that for g of x since it's a little bit more complicated to find. So we'll use this equation y equals mx plus b to find the equation of that line. And remember, m is the slope, so we'll use the 2 points we have, 1, 1, and 2, 0. Remember that we'll subtract the y-coordinates from each other, so we'll say 0 minus 1, and then our denominator is going to be 2 minus 1 times x plus b. When we simplify this, we'll get negative 1 over 1, which is just negative 1, so we'll get negative x plus b. Then we need to pick either point on the line, plug those in for y and x to solve for b. So we'll use 1, 1. We'll get 1 equals negative 1 plus b. Adding 1 to both sides gives us 2 equals b. So then we'll see that the equation of this line, g of x, this function, is y equals negative x plus 2. So we'll use that y equals negative x plus 2. Now we have the equation of f of x and we have the equation of g of x. That's all we need to define our limits of integration. So for the line region, the first thing we'll do is say that our lower limit of integration is 0, because this part right here, the lower bound, is the line y equals 0. So we'll put 0 there as our lower limit of integration. The upper limit of integration is defined by this function here, f of x, right? That's the upper limit. So we already know that that line is y equals x, so we'll go ahead and put x here. So that's how we integrate with respect to y. With respect to x, though, realize that we are integrating between the lines x equals 0 and x equals 1. Therefore, our limits of integration for x are 0 and 1. That, keep in mind, only gives us this part right here, right? The line region. We've only done half of it. Now we need to do the second half. So in order to do that, we have to add to this a second double integral to get the second half of the region. So in this case, we'll use the same function, 4x minus 1. We'll have dy and dx, but in this case, for our limits of integration with respect to y, our lower limit of integration will be, again, y equals 0, right? This line here, the x-axis, so we'll go ahead and put in 0. But the upper limit of integration is this line here, which is defined by y equals negative x plus 2, right? We found that here. That's g of x. So we'll say negative x plus 2 is our upper limit of integration. That's integrating with respect to y. Then when we integrate with respect to x, remember that now we're integrating between the lines x equals 1 and x equals 2. So our limits of integration with respect to x are 1 and 2. So that's how we set up for our integral, and that gives us the second half here of this triangle, the right half of the triangle. So now we have everything we need, and we can just go ahead and evaluate these double integrals. So let me give us some space here. So to evaluate the double integral, what we'll do is first evaluate with respect to y. We'll integrate with respect to y because remember, dy is on the inside here, so we integrate with respect to y first. So we'll go ahead and leave this outer integral because we got to deal with that later. Remember, when we integrate with respect to y, we treat x as a constant and y as the variable. So our integral becomes 4xy minus y. And we'll be evaluating that on the range 0 to x. We'll be plugging 0 and x in for y. We go ahead and leave our dx. Again, same thing here. We leave our outer integral from 1 to 2. We evaluate. We get 4xy minus y. And we'll be evaluating that on the range 0 to negative x plus 2. And we go ahead and leave dx there as it is. So now, let me give us just a little bit more space because we're going to need it. So now we can evaluate that definite integral there. So we'll leave the 0 and the 1. And here for this first integral, remember we'll be plugging in our upper limit of integration first, x. We'll be plugging in x for y because we already integrated with respect to y, so we're plugging in x for y. When we do that, right, we'll plug it in here and here, we'll get 4x squared minus y. So 4x squared minus x, I think I might have said y. So 4x squared minus x minus, then we plug in our lower limit of integration, and of course we'll get 4x times 0 minus 0, and then we go ahead and leave our dx. Then we add to that our second integral, so we've got 1 to 2. Now we'll be plugging in this upper limit of integration, negative x plus 2. So we'll get 4x times negative x plus 2 minus negative x plus 2. And if we had plugged in 0, of course we'd get, minus 0 minus 0, so that's just going to give us 0. I'm running out of space on the right-hand side, so I'll just go ahead and write that dx. So we need to simplify before we can move on to our next step. We'll have 4x squared minus x. This is going to become 0, this is going to become 0, so we just have dx. Then we have plus from 1 to 2 of, that's going to give us a negative 4x squared right here. Then we have plus 8x plus another x is going to be plus 9x. And then we'll have a minus 2 dx. All right, so now that we've plugged in those limits of integration with respect to y, we can integrate again each of these with respect to x and evaluate the definite integral the second time. So here, when we integrate with respect to x, we'll get 4/3 x cubed minus 1/2 x squared, and we'll be evaluating that on the range 0 to 1. Then we add to that, we'll get negative 4/3 x cubed plus 9/2 x squared minus 2x, and we'll be evaluating that on the range 1 to 2. All right, and just a little bit more room here. Okay, so now we'll go ahead and plug in our upper limit of integration 1 first, then our lower limit of integration 0. So 4/3 times 1 cubed is just going to give us 4/3, minus 1/2 times 1 squared gives us just 1/2. When we plug in our lower limit of integration 0, this will give us 0 and 0, so we can go ahead and leave that as it is. Then we'll add and plug in our upper limit of integration 2. So 2 cubed here, right, gives us 8 times a negative 4/3 gives us negative 32/3. 2 squared right here gives us 4 times 9/2 gives us 36/2. Then 2 times a negative 2 gives us a minus 4. So that's our upper limit of integration, and now we need to plug in our lower limit of integration, so we'll subtract, and we'll get negative 4/3 times 1 cubed is just 1, obviously, plus 9/2 times 1 squared is still 1, minus 2 times 1 is just a negative 2. Okay, so now that we've evaluated the entire definite integral, we can just go ahead and simplify, and I'm going to go ahead and put everything over 6 because we've got some things over 3 and some things over 2. So I'm going to find a common denominator of 6 and multiply here as I go. So 4/3 becomes 8/6 minus 1/2 becomes 3/6. Then we'll get a minus here, 64/6 plus multiply that by 3 and we'll get 108/6 minus 24/6 is what we get for 4. Then because we have a negative here and a negative here, we'll get a positive, again, 8/6. A negative times 3 gives us 27/6. And then a positive 2 is going to be plus 12/6. And if we evaluate that on our calculator, what we'll get is 18/6, which of course is going to be equal to 3. And so our final answer is 3, and that should make sense to us. If we look at the vertices of our triangle 0, 0, 1, 1, and 2, 0, we've got essentially in this first triangle over here 1.5 units of area, and in the second triangle over here another 1.5 units of area. So our area is 3. The area defined by the line integral that defines this triangle is 3. So that's it. That's our final answer. I hope that video helped you guys, and I will see you in the next one. Bye!